Hello? So, so weird thing is there's nobody, I cannot hear the, um, the organizers here, so it's gonna have to be me doing all the talking, I guess. Um, so yeah, I'm very excited to be able to present my work here at the RT-MFM. So it's a microscopie de fluorescence multidimensionnelle. Very nice YouTube channel with lots of very interesting talks. I'm Loic Royer. I am a group leader at the Zuckerberg Biohub, which is a non-profit research institute in San Francisco here. And today I'd like to talk about our new microscope, DaXi, which is a high-resolution, large field of view, and multi-view single-objective large microscope. And so, before getting into the topic of what you know what makes this microscope so special, I'd like to first introduce a little bit my team and what we do overall. So in my team here at the Biohub, we do a combination of computation, work on image restoration, image analysis, deep learning applied to fluorescence microscopy. And so we do a lot of projects there. We also build and design new microscopes, in particular light sheet microscopes. And this is what I'm going to talk to you today. And we also work towards answering some key questions in, developmental biology. In particular, we work with zebrafish model organism. And so this is something that will be upcoming in the next months once we get to finish the first projects in this area. So, if you look at the different projects we've done since the lab started, 4 years ago, we had some nice papers out. But today I want to talk about one in particular, DaXi, which is the single objective large microscope that pushes the limits in a number of characteristics. This is the work from Bin Yang in my team and many others. And so to get started on the topic, when you study, developing air organisms, when you try to understand how an organism develops from a single cell, eventually for this cell multiplying, dividing, forming tissues, you need to be able to have extremely good microscopy to be able to follow the cells, follow all the cell divisions, because at some point you have tens and hundreds of thousands of cells. And so you need to be able to image at very high speed, you need to image at very high resolution, and to do so, you need better microscopes. You always need better microscopes. Microscopes are never enough, never good enough when you tackle such difficult problems. So why light microscopy? It's fast, it's gentle, it's volumetric. And for those that don't know how it works, you basically create a light sheet from an illumination objective, and then you detect the fluorescence coming out of that plane with a detection objective. And so the beautiful thing about this is that you illuminate only what you look at, and you only look at what you illuminate. And by moving that plane rapidly in the Z direction, you can obtain a 3D scan of your sample and therefore a 3D image. And you can obtain these images at a rapid pace. In our case, typically between 20 to 20 seconds and a minute, depending on the microscope, the type of legit microscope, and depending on the particular parameters of imaging. And very important, by doing so, by only illuminating what you look at, and by only looking at what you illuminate, you also reduce the amount of light you have to, the dosage of light you have to impose on your sample, and therefore it's live longer in the microscope. In fact, we rarely kill our samples these days. They often come out of the microscope and scats. And we also reduce photobleaching, which means that we retain very strong signal throughout the whole imaging, which is also very important. So when you look at historically what has happened with light microscopy, and if you look at one branch of that evolution, there's been incredible microscopes in build, starting with the first single objectives, single the illumination and single detection objective lecture microscopes. That was then extended to be able to image from both sides of the embryo and illuminate from two sides. So then total of 4 objectives, 2 detection, 2 illumination objectives. Fantastic machines. We have one here at the Biohub that we re-engineered. Beautiful systems. We do routinely biology with them. And then of course, you have very creative solutions that have been developed where you can use the same objectives for detection and illumination. And in that extreme, I think one of the most amazing machines out there is the machine that was built in the Keller lab in Geneva, where you have 4 detection objectives, 4 illumination objectives, and all of them running at the same time. Give you an unprecedented, spatial-temporal resolution. And so these are really fantastic machines. But of course, it imposes a little bit of a hurdle for the experimentalists to be able to mount the samples in a way that accommodates all these objectives surrounding it, right? So, and this is maybe not a natural thing for biologists to do. So if you look at 2 detection and 2 illumination objective microscope, this is what we have at the Biohub. We have and this was built in the last 4 years, and it's actually been built, the first 3 years of the lab, and then we've been using it, already for the past 2 years routinely. And so, very, very nice machine, and we use it, every week, but it still has some limitations in terms of sample mounting, and we wanted to facilitate that. So, what you get from that is the kind of data sets you can get from these instruments are beautiful data sets such as these. This is something I acquired together with the team of Philip Keller in Geneva. Very fantastic, beautiful data set, exquisite temporal and spatial resolution. But when you look at and then me, my team, we also do the imaging, but this time we actually use a zebrafish as a model organism. So this is early zebrafish embryonic development, where you can see the nuclei inside and the mesoderm in purple here. Same instrument, very beautiful images. You can accommodate almost a cubic millimeter of tissue in these machines, but again, a little bit tedious to mount the samples. This is how it works. So to mount the samples in such a kind of 2 detection, 2 illumination batching microscopes, you have to embed your embryo inside of a cylinder of agarose. We use special tubes in FEP, a material that is almost has almost the same refractive index as water. The embryo is embedded inside, and the agarose is kind of stabilizing the sample within that. But you can see there's a lot of parts to this mounting. It's a little complex, and makes it a little bit difficult to do. It takes it takes some time for, in this case, Merlin Anger in my team to do that. We were lucky to have a very great team of bioengineers led by Raphael Gonen-Schulberg that helped us 3D print very nice parts to be able to hold all these things in place. But it's still it remains a challenge to do this work. And then you could put multiple samples, but the complexity increases, and the question is, can we do better? Can we do simpler? Can we do something that's more natural for biologists for mounting their samples? So this is what we attempted to do, building up the work of others and then developing it further. So this work was led by Bin Yang in my team, and it was a very nice collaboration with Andrew York and his team at Calico, where they came up with this beautiful objective with 92 that made this work also possible. Many people, as you can see, involved in this work. I will mention them throughout the talk. So, what is single objective light microscopy? Well, the idea is very simple. So it's easier to mount samples on horizontal surfaces, in this case transparent surfaces, cover slips, for example, and have just one piece of optical glass interfacing with the sample. Therefore, you ideally want the best possible objective you can get with the highest possible NA, and get all the light you can get from the sample, and at the same time bring the light sheet itself to that same objective. If you can do that, then automatically, you get much better ergonomics, right? It's a simpler sample mounting procedure. And these ideas were developed already in 2008 by Dunsby and extended more recently. In particular, Bin Yang, who was at the time not yet in my team, but in Bopang's team, developed some very nice optical tricks to be able to push the NA of these of these systems, so that we could not compromise resolution in these oblique configurations. And more recently, in the team of Felter Fiolkau, they developed ways to push the NA even further, pushing the limits of that for single cell imaging. Really beautiful work. So let's go through how does that work, and how things work in the traditional light sheet microscope, and compare that with a single objective light sheet microscope. So in the traditional light sheet microscope, you have an illumination objective that produces a light sheet. You have the sample here in blue. You have the detection objective that detects the plane that is illuminated. As in any microscope, you have a tube lens, and then you form an image, a virtual image that is elongated due to the change in magnification. And you would typically put the camera there and basically get your image. And this is how standard light sheet microscopy works. Now, what you can do instead is assume that you have the means to bring the light sheet through that same objective, to that detection objective, which we usually call the primary objective. Then what happens is in the virtual image, the part of the sample that is illuminated is oblique, and it's actually even more oblique because of the elongation of that virtual image. So you can't possibly put in a detector there. The angles are just wrong. You would have total reflection or anything. It just won't work. You would lose a lot of resolution. It's just not possible. So what you can do instead is put another microscope in some sense, but this time that would undo the effect of the first one, and you can recreate the light distribution of the sample, and that light distribution now is purely virtual. There is no object there. It's similar as what happens between the two glasses. But the beautiful thing here is that you can put a third microscope in some sense that will then be imaging at an angle. And you can't possibly do that with the original sample because there's already an objective there and so the two objectives would collide. But by using this trick called remote focusing, we can recreate that sample virtually and then re-image it. So of course, we're talking about 3 objectives instead of 2, but the beautiful thing is we're pushing the complexity away from the sample. So the thing to understand here is that, sure, there's a little bit more optical complexity here, but the trick is to put that complexity away from the sample, away from the biologist in some sense. The biologist will be able to mount the sample in much easier ways than if one had to accommodate for a multiplicity of objectives surrounding the sample. So a single objective is in contact with the sample, in contact with the biology, and all the optical complexity is pushed away from that. And there's more benefits than just that. Actually, the kind of NAs we can achieve, the detection NAs we can achieve are actually higher. We'll see that in a second. So this is what Bin Yang did when he was in Bo Wang's team at UCSF. And this was published nicely in 2019, Nature Methods, where they could image, in a small field of view cells. And so the trick to be able to collect all the light and maintain, high NA detection, which was kind of the breakthrough that being introduced, is to use a water chamber that will, essentially create a index mismatch that will basically bring the light bring the light in a way that it can be entirely, channeled through the tertiary objective. So a beautiful trick that made it possible to avoid losing some of the k vectors for the technically minded among us, and get all the resolution out of the system. Because of course it's a difficult thing to bring, when you're doing oblique detection, you need to make sure that you bring in all the light rays from all possible angles in. So that was a very big success, and great work by being in Bo's team. So, but now the question, when Bean joined my team at the Biohub, we're thinking, okay, so what are we gonna do? And one thing that, because we wanted to image a zebrafish, one thing that became clear is that we need to image much larger samples, and we wanted to retain this same ergonomics and simplicity that single objective light jet microscopy had introduced to the field. So, can we image much larger samples without compromising speed nor resolution, right? So can we do that? Can we push the boundaries without losing anything? And this is so this is really what Bean set up to do with DaXi. We were thinking about a title, a name for that microscope, and we thought, well, to recognize the multicultural nature of the team. We have all sorts of nationalities as part and ethnicities part of the team. So I thought, yeah, we should try to be inclusive and come up with some very nice name. And so Bean thought about DaXi as a very nice way to communicate what the microscope was about. And the microscope is large, can image. It is large, but it can image large samples. And it can image them in a very fine manner. And so that's how we came with this name that comes from Mandarin Chinese, Dashi, actually. If you pronounce it correctly, it's pronounced Dashi, large and fine. And so this is actually a picture of the setup. In a schematic way, this is how it's set up. The key innovations of this microscope are that we have a new custom design tertiary objective, we have increased scanning range, we have dual illumination and essentially dual view imaging, and we have improved sample ergonomics. And as you can see, we have a number of optical systems laid up here together in both an illumination and detection path. And I will go through a little bit the details of that as we go forward. So the key features, as I said, is first, it's a single objective light jet microscope. Second, it's high resolution and large field of view. It has fast and long scanning. So I mean that we can scan very along one dimension. We can scan very long distances and not compromise any speed. And because the samples that we're interested in are large, they tend to make it difficult to image with a single view. So we have multi-view imaging with dual illumination. So let's go through the single objective aspect of things. So how do we do that? So again, the reason for single objective light jet microscopy is that the sample mounting is simple through this oblique illumination, right? So basically this oblique detection via remote focusing makes it possible to get very nice, quite high resolution images because of the high NA of the primary objective. And the amazing thing about this is that you can actually, because you're mounting the sample on a horizontal surface, which can be in this case, for example, a dish with a glass bottom, we can image multiple embryos at the same time in a very easy manner, right? You just take some agarose, pour it inside of your dish, use a mold maybe to create, different cavities, put embryos in these cavities, which is a very simple thing to do. You can fill up with a lower density agarose. And then now you can achieve, you can do that, you can prepare that pretty fast, right? Because you can prepare a lot of these things in advance. And, once you have the embryos available, you can set that up pretty quickly. And this is much easier than any other kind of multi-embryo mounting schemes that would involve perhaps tubes and such. and more importantly, it's closer to what biologists have been used to do for the past 100 years or so. Um, Relying on gravity, relying on horizontal surfaces. This is really, we believe will make it easier for biologists to adopt this technology going forward. I mean, for me, like, hiring biologists in my team has been really important to understand, what matters in some cases. Like, I think, having this ready to check of, having people, that experienced in the sample mounting and basically and in biology in general, quote unquote, has helped, to readjust the way I think about a microscope in some sense, because I came from a little bit more technological background, building and designing these systems. But I think, it's very important to have this reality check from time to time. So with this, we can do this 9 embryo at a time imaging, of course, sequential imaging, one embryo at a time. So because the microscope is rather fast, we can do that in rather quickly. And this is the result of that. So we can image at 2.5-minute intervals, which is actually pretty good. And that means, each embryo is imaged at 2.5-minute intervals. And here you see basically 9 zebrafish embryos developing. We focus on the tail extension and tail bud here, and you get very beautiful images. Of course, not all embryos are perfectly oriented. Maybe some might eventually die. It's not the case here, but you could imagine that you want to study something, and you need to have enough replicates. And you might want to only keep some of these videos, but at least it makes it easier to do this kind of high throughput experiments. You could imagine putting different drugs for different embryos. You could imagine having even more embryos than that. So you can start to imagine that all the things you could do in terms of high throughput microscopy in biology here with embryos, something that's been a bit harder to do with light sheet microscopy because of the way things are set up in a standard light sheet microscope. So of course, ergonomics and be able to look at multiple embryos is important, but if you lose resolution, or if you cannot image the whole sample or all the parts of the sample you care about, then you're making a compromise. And what we wanted to do is not to have a zero-sum game, but really gain on all fronts simultaneously. So can we retain the high resolution and increase the field of view and the imaging volume? Can we do that? To do that, we basically use a new objective that's called the Snouty 2, and essentially it's a very special optical device. So what it does is it's an objective that has a working distance of 0. And it basically what it does, it has the key thing, it has this sliced, so the front face of the objective has been engineered such that it can approach the secondary objective where the actual virtual image of the sample is located, so that you can actually re-image that virtual image at an angle, and the angle can be up to 55 degrees here. And so by doing that, and the key thing of that new bigger and better objective compared to the previous version, which was a Snouty version 1, is that it has a working field of view of 450 microns. In fact, it can go beyond that, but of course, you start losing a little bit on the NA. So it's always a little bit of a trade-off. You kind of resolution starts to roll off a little bit on the edges, but 450 microns is kind of where you have the guaranteed 1.0, but you can still get pretty decent images beyond that. So fantastic objective by Alfred and Andy at Calico. They did a great job there, and we got one of the first versions of it to build DaXi. So really great thanks to them. The really cool thing about this objective is it's 1.0 NA, so it's really strong light connection and resolution there. And what's important here is to understand that this is really important. In many cases for biology, when you really need to to look at things that are actually very finely resolved, you need to be able to get to such NAs, especially. So that's very true for single cell imaging, but even for embryo scale imaging, we do need to be able to see membranes, for example. We do need to be able to resolve nuclei, especially resolve that, for example, two nuclei are not one, or that they be able to kind of tell apart things. Because if you want, for example, to track cells over space and time and their divisions in very tight regions of the zebrafish embryo, which is something we're interested in, you need as much resolution as you can to get crisp images and also very good Z resolution. So overall, NA is always important. It was always a little bit difficult to push beyond 0.8 NA in light microscopy, at least for embryo scale imaging. But now with this objective, it's really easy. So what's the performance of this system? So the optical performance of DaXi is the following. So in terms of imaging volume and field of view, so the field of view is 420 microns along what we call the X prime direction, which is kind of this oblique direction, and along the Y direction, which is perpendicular to that, it's 800 microns. So we typically use half of the sensor, and that actually also gives us a little speed advantages. And once you have that, then that represents about 300 microns along the Z direction, which is kind of along the axis of the primary objective. We can then think about the X direction, which is in the scanning direction. In this case, if we do Gavo scanning, we limit it to 300 microns. But if we use a new way of doing scanning, which I'll explain in a second, we can actually do unlimited scanning. The only thing that you have to pay for is the temporal resolution. So you can scan for millimeters, but then you will have to basically accept the fact that your temporal resolution is going to be affected by it. So, but a very natural trade-off in microscopy, and one reasonable to live as such. In terms of resolution, we have looked at the PSF. Actually, we have looked at the PSF in the whole volume and characterized it. I don't have the data here, but kind of if we look at one beat, in the reasonably central position, we can see we have a resolution that's around between 390 and 440 nanometers, and in Z it's more like 2 microns, and that's actually pretty stable throughout the imaging volume. I don't have the data here, but we have done that in the past months for a resubmission of our paper. So very nice optical performance overall. And one thing to notice here is that the PSF has a slight angle, and that's because of the the oblique optics. But when we measure our resolution, we align, of course, to the to the main axis of the PSF, right, to get an accurate measurement of that resolution. And as as I said, we have unlimited scanning when we do the trick I will mention in a second. So when you do the imaging of, for example, of a 2 days post-fertilization zebrafish larva, where all the nuclei are labeled with and cherry, you get this beautiful image. You can see the somites there, and so this is a still image, but we also have videos of that. But here it's just to give you an idea. Because we have a single objective, of course, on the other side of the we get a good image on one side of the embryo, and on the other side of the embryo it starts to get a little bad. But that's very natural for that microscopy. No surprise there. Um, if we look in more detail, you can see, the exquisite resolution we get throughout the sample. And this image can be acquired, it's not acquired with any tiling, so this can be acquired as fast as 15 to 20 seconds, depending on the parameters. So that's pretty cool. And yeah, it's as you can see, we can nicely resolve many of the nuclei. Completely different type of sample. We collaborated with Tom Kornberg at UCSF and one of his postdocs. And then we basically looked at this oocyte development, and they were interested in a rare event during this process, and they needed to be able to look at a very wide field of view and very large image volume to not miss that rare event. And so we collaborated with them, and as a side effect we got this beautiful video that just really, for our purpose, illustrates the large imaging volume that we can achieve. Here, pay attention to the scale bar. That scale bar is just 200 microns. So you can imagine this is almost 3 millimeters in one dimension. So, I mean, you can imagine you can also imagine the size of the data that this entails, right? And so, of course, the image processing and image analysis and the scale of the data we're talking about here are truly monstrous. We got an email yesterday from our IT department saying, "Oh, you guys have been acquiring, I don't know, many tens and tens of terabytes in the past 2 weeks. Is that normal? Is this continuing?" Well, yeah, this sort of things happen. So yeah, the data scale is only getting worse, frankly. So what about imaging speed? So that's a very important thing, right? If you want to do live imaging, which is something we really care about in the lab for our purposes, you need to make sure that this instrument is very fast. And so we were facing some issues, and we found some nice solutions. So we have this approach for fast and long scanning. Let me explain. So when you do single objective microscopy with large samples like a zebrafish larva or embryo, you need to scan quite a big a range. So you need to be able to image a fairly large volume. If you use galvo scanning, you're limited to 300 microns, because that's you can see it from essentially the range of scanning that is available that's provided by the objective itself. You can't bring the light sheet outside of the footprint of the objective, right? It's just you can't move that light sheet further than that. And the angle also doesn't help much, right, for scanning, because of course it just creates the awkwardness in the volume that you're actually illuminating. But if you sample, if you do scanning by using the stage instead, if you move your stage, move the sample through the light sheet, and instead of moving the light sheet relative to the sample, you move the sample relative to the light sheet, and essentially you move the sample. The only thing that moves is the sample itself. Then it's much easier. I mean, it's really cool, because then if you can do that, then of course you can keep your light sheet along the axis of the primary objective. You can basically avoid exploring areas of your imaging volume that are perhaps lower quality because of the optics. You can keep everything centered, which is good from an optical standpoint. And if you do that, then you can get the best possible images. But that again assumes that you can move your sample through your light sheet, and you don't have to pay any price for that, which is actually not the case. By default, what you can do, for example, is, okay, I'm gonna move my sample stepwise because I want to avoid moving the sample while I take an image. And then I move the sample, and I take another image, I move the sample. So you need to stop and go with your stage. You need to move your stage, stop the stage, move the stage, and that is not very good because it's very slow. You have to settle. The stage has to settle, and it's a fairly large piece of metal that has some weight to it, some inertia, difficult to start and stop, right? But if you can, yeah, but you still want to do stage scanning because it forces such a large field of view, such a large scanning distance and so on. So instead, what you could do is just continuously scan your stage. But the problem with that is that during the time you expose, you actually have some motion blur, right? Because the stage is moving, so the sample is moving relative to your light sheet while you're taking an image, introducing motion blur, and we spend a lot of work and time and effort to have high resolution single objective light sheet microscope. So it's certainly not time to lose that resolution by moving a stage continuously. So that is not, that was not a priori a solution. Another possibility is to do continuous scanning and then strobe the laser light of the light sheet. So to avoid the motion blur, let's just gate by illumination. So let's just illuminate for a very short amount of time, and if we do that, then we freeze essentially the sample for a short amount of time, and the camera might still expose for some time, but at least we know the effective exposure is not only defined by the laser's pulse, the short duration during which the light sheet is illuminated. This can be a good solution, but this again you have to pay. You have to pay for it. Yeah, and you have to pay in terms of photo damage, because the instantaneous power going through a sample now goes through the roof. Right now, for a very short amount of time, you're sending a lot of photons through your sample, causing photo damage, causing photo bleaching, and so you really, and even if you do that, you still have the problem that the motion blur is not completely eliminated, because you still have to expose for some time. You still have to have some illumination for some time. I mean, if you reduce that time to 0, the instantaneous power goes to infinity. So you don't want to do that. So you'll have to use, so it could be a solution, but you're paying for it, in one way or the other. So is there a way to make this work without any compromise? So what we designed is this light sheet stabilized scanning, LS3. So it's the way we think about it is as fast as a galvo and as far as a stage. The best way to drive a stage is to move it continuously. So we do continuous stage scanning, but we introduced a trick whereby we stabilize the light sheet relative to the sample. So we move. So with stage scanning, the sample is continuously moving. But what we know now is that we move the light sheet during the time we expose. We move the light sheet at the same time, at the same speed, thus canceling the relative motion between the light sheet and the sample. So now the effective scanning is as if we were, stepping the stage, but it's actually not the case. We are actually moving the stage continuously, but the galvo is doing the stepwise motion. But because the galvo is so fast, I mean, the dynamics of a galvo are much faster than a stage. So it's a much higher bandwidth mechanical actuator, so you can actually move it much faster and it settles much faster. So you can actually do this stabilization, relative stabilization, and effectively cancel out any movement during exposure. And so what happens in the end is we have this continuous stage motion. We have light sheet compensation during exposure, and then there's always a little bit of a time after exposure during which the camera sends back information to the computer. There's always a little bit of dead time, and so during that dead time, we actually fly back the light sheet to be able to redo a stabilizing motion for the next image in a stack. So a stack, a 3D image is made of 2D images, and we do this compensation and flyback for each image, and this works really well. So yes, it works. So this is an example here, very fast imaging. You can see the cells dividing there, and at the same time we can image the whole thing. This is basically the tail part of a zebrafish embryo. So I think this is one of the first videos we made. Actually, by now the quality has improved a little bit, But it's a very nice video because it has actually a pretty nice resolution, and you can see the temporal resolution. And here, importantly, we have actually two views, and I'll talk about this in a second. So another video, more recent actually. Perhaps the resolution is a little, the quality, the set was maybe a little bit more mature by then. And very nicely we can, we're following the tail bud, growth and the tail expansion. Somites are forming there. And the video keeps going on. We have two slices on the, on the right side. We have a color max projection on the left side, and so you see we can image fairly fast for a long period of time and get this very beautiful image. And this is done with stage scanning, right? But stage scanning with this LS3 trick. So what that does is really, like, we can scan as fast as a galvo and as far as a stage. And there's basically combine the best characteristics of both. As I mentioned at the beginning, we have we're interested in looking at embryos, particularly zebrafish embryos, and so having a single view on the system is not enough, because light has a tendency to be scattered and suffer other types of aberrations that it enters and leaves the sample. So when you think about your sample and your light sheet entering it, and in a single objective configuration, it would look like this. If you were to be able to send the light from two different sides, that gives a really strong advantage, because the truth is that for the same point in the sample, there are and for two different views, the amount of scattering and aberrating material on the way that affects the light sheet propagation can be different. And so some an image acquired with the light sheet at one orientation could be at a given location better than for the other view. So and here we really have only illumination diversity, because the detection cone is the same. So the light on the detection side goes to the exact same material. So as you can see here, so it's really about illumination, the difference in illumination. And we do actually see a very strong effect on image quality if we can actually combine information from both views together, right? And here in this case, for this blue point, clearly the information from the right view, from the view on the right, would be actually better. But it might be a different story in different parts of the sample. So we need to do something smart about combining the information. So how do we actually do that? How do we actually, how did we design the microscope so we can flip the orientation of the light sheet? And so the way this works is we have an image flipper. Essentially what that does is it basically, it's an arrangement of mirrors with two galvo mirrors that are actuated, that can take two positions. And essentially by reflecting either an odd number of times or even number of times the light, we can actually flip everything. So we not only flip the light sheet, but also we flip the detection. So both the detection and illumination paths get flipped. And so essentially it's as if we were flipping one part of the microscope relative to the other. So on the detection path, as well as on the illumination path, we can do that. And so essentially, it's really as we were flipping, one part of the microscope relative to the other. And so basically, you get a situation where the two overlapping volumes that can be imaged are not perfectly overlapping, because there is, of course, geometry. The geometry is different, so there's parts that are only imaged in one or the other. But there are a large part of the majority of the volume gets an overlap from both, and so as I explained before, we basically can acquire these two images and then combine the information of these two images into one image. Here, an important thing to notice is because we're using galvo mirrors, we can do that very fast. The flipping can happen very, very fast. And another thing that's very important is that we're actually not losing any light, right? We could be doing some splitting, right? We could have done a system where we could have split the light and maybe 50-50 or some other tricks, but here we put a lot of work to get high end detection system with very high light collection efficiency. So it's not it was certainly not a good idea for us to then start losing light when for the multi-view. So here again, the objective was to not compromise another dimension for this one, and so we actually managed that using this flipping system. So here is what it looks like. You have basically two views, and you can see that different parts of the sample are lead to different image qualities for between the two views. So there's parts of the view one that are better quality than parts of the view two. So it's definitely complementary. And so we can fuse that with an algorithm that we designed, a very simple, content-aware fusion algorithm. And in more detail, this is how it looks like. So if you have, for example, here are a number of examples where, for example, view one is better. So on the examples on the left side, you have view one is better, whereas the examples on the right side, it's view two, which is better. And you can see that clearly in some cases, some nuclei, for example, here are gone from one of the two views, but we can actually combine the information to get better images. And so hence the importance of doing that fusion. And again, the algorithms are very standard by now. There's been a lot of work in image fusion. Nothing very special there. So we're super lucky to have a very good relationship with Larshi, who had visited our lab, and we were aware of his amazing work, with his microscopy nightmares, quote unquote. And so we basically talked to him, and he was very excited to contribute. A beautiful video, which here I present just a part, where we can see here our flipping mechanism, between the two views. It's actually the real microscope really looks like this. This is exactly how it looks like, and yeah, this is relative then with multiple samples. Here, for example, we have multiple wells. We typically right now use only one well, but you could imagine how you could scale that up and have high throughput. And this is the galvo that does the scanning and compensates the movement of the stage again. Yeah. So as I mentioned before, there was a lot of effort put into designing software to process and render these images, because of course you can imagine that the scale of the data now is as you can since you can scan along one dimension almost for millimeters, of course the amount of data you're generating here is just nuts, right? So and when you think now that this is live imaging, maybe every 20-40 seconds, depending on the size of the sample you're looking at, you're generating a lot of data. So it's really tricky, and so we put quite some time. So I started writing a library called DaXi to help people with in the team, especially the biologists with the two microscopes we had, and we extended it to DaXi. So now it basically can process the data from true detection, true illumination objective light chain microscope, but also from our single objective light chain microscope. Now in my team, Jordao, Brangantini, and Amit Solak are basically helping develop this further. Especially Jordao has been putting a lot of work recently to extend it with support for Dask and other technologies that make it possible to run this on GPU, on multiple GPUs, potentially on multiple machines, and so on and so forth. So have a look. It's on the GitHub of the Royer lab. It's called DaXi. Yeah, I think I've come to the end of the talk now. I hope it went well, that, there was no glitches on my first, YouTube streaming thing. So it took a little bit of preparation to get it all working out. I hope I hope there is someone listening on the other side, because I actually have no way of knowing what's happening on the other side of this. Um, I'd like to thank, of course, everybody at the Biohub that has been supporting all this research, and in particular my team, Merlin, Rofumi, Raphael. Raphael is not in my team; he's a bioengineer, the lead of bioengineering at the Biohub, but he's been, personally involved in helping us with some of the sample mounting gadgets that we're using. Really amazing engineer that's been helping us a lot. Jordao has been doing a lot of work on DEX. Um, and rendering and more for this project. I mean, Chansolak is our software engineer in residence, doing fantastic work. Shruti has been doing a lot of work helping us with the fish preparation. She's taking care of her fish and more. And Merlin has helped a lot, been doing the imaging. On the other side, we have, of course, this was a great collaboration with Andy York, Alfred from Calico, Tom Kornberg and Wan Peng Wang were basically great collaborators on this side collaboration. And we had some very nice conversations with Reto Fjolka from UT Southwestern. And of course, Laishi made this beautiful video that you saw. Yes, that's it. Thank you very much for your attention. And I will try to figure out if there's someone on the other side of this, and see if there's any questions that need to be answered. So I'm not sure how this works out here, but um, I'm on the chat. Idea. Yeah, so I'm French actually, but I didn't speak in French because I'm not used to speaking in French. Actually, frankly, I'm forgetting my French. So my webcam is blocked. I don't know why that is the case. Uh, hmm. Oh yeah, I see. There's no movement on the webcam side of things. Well, that's okay. The slides are more interesting than any questions at this point? If you have questions, you can type on the chat. I'm just looking at it. I'm monitoring the chat. The particular kind of, I mean, I don't think it's anything very special for the cover. So the question is, what kind of cover slip do you use on the sample? So actually, we avoid putting cover slips on top of the sample. So what we do is we typically use little, wells. So I'm not sure that's the correct word, but we're using little um, yeah, some sort of, like you saw, the little wells that have basically a glass bottom, and the glass bottom is, the typical cover slip thickness, so that you can match the optics, with what the objectives are used to use. So yeah, so it's not, I mean the easiest is to check the paper for the actual details. I don't have on the top of my head, I don't have to put the details about the particular mounting receptacle we use. Another question is, are the three objectives linked, or can we change the objective number? There is some linkage, because I mean, it is unfortunately, like, we need to find objectives that play well together, and there's definitely a lot of parameters to adjust, and make sure that they play well together. And so it's a little bit of an art. So there's actually a very nice website from there's actually nice resources out there from Andy York, for example. He has a GitHub repo where then you can play with different configurations of objectives, and they've explored that space a little bit. I think there's another paper. I can't remember the reference right now, but there's some people that have been designing tools to be able to figure out. Yeah, I'm actually coming to MultiView. Actually, I will be coming to. So another question is, will you come to France from MultiView? I will. And I'm looking forward to. So I won't be actually. Interestingly, I haven't been asked to talk about this microscope. Sorry, I will talk about some other things. But I've told the organizers that I'm very happy to talk about anything. I will be there almost the whole time. So um, very looking forward to meeting all you guys there. Yeah, someone said Sophie Allard said the PSLs are amazingly small. Thank you. I don't know if no, I don't know if they're amazingly small. Actually, they're actually better now because we have improved a little bit on some things, but and they might even get better in the future. So that's very possible. Yeah. Any other questions? Yeah. So I will let the organizers tell me. Oh, another question. Is the system stable or must it be reliant before each manipulation? Um, I I think it's a prototype. I mean, it's not a commercial system, of course. So you have to do a little bit of alignment, but I don't think you need it before each experiment. So I think maybe Bean does it once a week or once every 2 weeks, but and of course he checks if it's in a good state and so on and so forth. So of course like if you're familiar with my work, we're definitely looking into applying some of these autopilot ideas and have automatic realignment and during imaging and before imaging. And so this is something we're actually working on slowly because it's important. But the truth of it is um, because there I think it's a much more stable system than a kind of multi-objective system because you have less optics in contact with the sample, and so it's easier actually. I think it's easier. Yeah, yeah. So I think it helps because then by moving the complexity away from the sample, you also put some of that complexity in a safer spot from a drift perspective and from the thermal influences of the sample. Because of course we're playing tricks with the sample, making sure that it's at the right temperature. So flowing some warm air there, and so like that can be a trouble. That can cause trouble, but that's away from most of the optics are away from that, and it's just the primary objective. So that helps to stability. Any other questions? I will let the organizers tell me when to start. Okay. So I'm sorry if the video, so my webcam was not working apparently. I mean, it was working, but somehow got frozen. It froze. But anyway. Okay. I think unless so there's a question, do you have the idea to make to make a partnership with commercial providers? Um, yeah, right, not so much, but anything is possible. Yeah. Thank you. I think the organizers are starting to signify that we should end this. Thank you everybody. Thank you for your attention, and thanks for the organizers for this very nice opportunity. Christian Rouvière, Brice Roncin, and others. Thank you. Bye-bye. I'll stop the diffusion now.